Okay, can we see it?
Yes, sir.
Okay. Okay, good afternoon, ladies and gentlemen. It's the last session, okay, of this workshop number 5. We come to an end. Okay, the topic I would also like to present, it is not directly related to earthquakes. I will say a few words about hastening of concrete dams. Of course, when you do a hastening, if you make modifications of your dams, you also have to make a reassessment of seismic safety. And I would like to talk here about concrete dams. And first, I would like to say a few words about the key issues in dam hastening. Okay, what we would like to achieve if we hasten a concrete dam is to have a good bond between the old and new concrete to achieve a monolithic structure. We have to do a stress and deformation analysis, static loads and earthquake action. We have to do stability analysis. We have to look into the contact between new and old concrete. We have to look in the heat of hydration of new concrete. What is the effect? Probably we may have to look in the drainage of the interface between old and new concrete. And again, we have to look in the water tightness in dam foundation because we have a higher head. Okay, so these are some of the key issues, and I would like to discuss it briefly. Why do we discuss the dam hastening? I understand you have built already most of the dam. You
बोलो क्या हुआ?
your microphone.
कुछ नहीं,
खाना हो गया?
खा लिया मैंने पास्ता।
कैसा लगा?
बढ़िया लगा।
माइक्रोवेव करके खाया? कैसे खाया? जो उस रेस्टोरेंट से मंगाया था,
Mute their microphone,
एक दिन
please.
रेस्टोरेंट से मंगा के खाया था ना, ये वाला सेम ही बना कुछ वैसा।
उससे बेटर ही लगा मुझे।
Can I request to the participants to mute their microphone?
हाँ, वो तो कड़क से ही हो गए थे वो तो।
Okay.
काफी हेवी है वो, ऐसे देख के थोड़ा सा खा के बहुत पेट भर जाता है। उसमें चीज भी बहुत पड़ता है ना इसलिए।
Okay, mute your microphone, please. What I wanted to say is in India, okay, not only in India, actually even more in the Western countries, there's a lot of opposition for new dams. So one of the, let me say, possibilities or where we have a bigger chance or less opposition is that you do some hastening of existing dams. And it turned out that this is quite economical, and we have done a few dam hastening projects in Switzerland, and I feel probably this is also a good option for India if you have to increase your, for example, energy output on a short, relatively short notice. So hastening is actually very, very interesting. Okay, if we look into some existing dams, we may have back developing in concrete dams, top gallery dams, some cracks here are mainly due to temperature effects. Okay, we have some leaching, or we can have alkali aggregate reaction, basically swelling, or we can have sulfate reaction in a concrete, which is also causing swelling, and we can have frost temperature, which causes micro cracks, basically in the surface. It will damage the surface concrete. Okay, so we have aging of mass concrete is one factor which is important, which has to be considered. What is the basic requirement? If we do some modifications of the dam, they are the following. Number one, the dam must satisfy today's design criteria. That means the hydrological, for example, PMF, and seismic safety evaluation earthquake design criteria. Often the seismic load scale has not been considered properly in all the dams, as I mentioned already. So it is really necessary to do when the seismic analysis if you are doing dam heightening project. We would like to achieve number two, that the Hayton Dam to act as a monolithic structure. I've mentioned that before. Number three, safety assessment of old dam according to today's requirement. The question is, can the old dam carry the extra load? It is important that we use today's design criteria for old dams. Some people may feel if you do some modifications on your dam, you can still stick to your old design criteria. I think this is not what we think is correct according to ICOD, but of course, for some dam owners, if they want just to do the minimum, they may be tempted to argue in this way, but you should not accept that. Number four, safety of existing dam usually decreases, of course, if you do some heightening due to the extra water load and dead load. It is clear if you heighten an existing dam, if you do not really strengthen the overall dam body, just add some extra height on top, your safety will go down. It's clear. Okay. The next point, the performance of new concrete parts and the interface have to be monitored by additional instruments. Okay, there are some questions how these two types of concrete interact. And the last one, layout. It could be necessary that additional inspection, grouting, drainage galleries at the interface may be needed. Okay, so you would have to look at these issues as well. And of course, if you do some dam heightening, it means you also have to do some modifications, usually with your spillway. If it is a gated spillway or ungated spillway, you have to modify that. So it has some implications also, not only on the dam body, but also on some other parts. Okay. Why do we need dam heightening? I must say, or what I have mentioned a few times, when dams are properly well-built dams and well-designed dams are properly maintained. They have a very long, I've written here, unlimited service life. I would say the service life may exceed 100 years if you do not have really one deficiency, like aging, I've mentioned, like alkali, silicate reaction or sulfate reaction, something like that. Number two, the use of a dam and its reservoir may change during the economical life, and extra storage may be needed, for example, due to sedimentation. We have that in Iran, one dam project I'm involved. The sedimentation level is 100 meters thick, actually, at the dam body, which the dam is 200 meters high. Okay, or we need some extra volume in the reservoir for flood control. Okay, we can say extra retention volume in an existing dam, which we have done in Switzerland, or we need some extra water storage. So there are a number of reasons why people feel heightening of a dam is a viable option. In Switzerland, dam heightening has become an interesting option for optimizing power production, as the dams are very safe, already due to conservative design criteria, and the environmental impact, okay, in steep valleys, I must say, is minimum. In some other parts, I've been involved in a project in Sudan, between Blue Nile and White Nile. It is absolutely flat. They have some cataracts, and I was involved in one project. They heightened the dam by 10 meters, and the reservoir area doubled. Basically, the reservoirs are becoming very large, from 300 square kilometers roughly to 600 square kilometers. A huge increase only due to 10 meters, whereas in Switzerland, if we increase 10 meters, maybe we only need a few hectares extra land. I will show one example. Okay, what are the some technical aspects with the hastening at the interface of old and new, about 0.5 to 1 meter of the existing concrete dam has to be removed, as this layer may be damaged by micro cracks due to temperature, climatic conditions, and depending on the properties of the mass concrete. Okay, we also have to look that we do not have any buildup of pore pressure at the interface between old and new, and it has to be checked by drainage, because if you have extra water pressure, it may create some unsafe conditions. Number 3, old concrete may be permeable, and water may circulate along lift and temporary construction joints. So therefore, water tightness has to be achieved, for example, by grouting of the old concrete. So it is required, if you do tightening, that a clear concept be established. Also, the extra hydrostatic pressure is depending, of course, how much the dam will be hastened. We may require modification in the grout curtain. And I would say we feel that without changing basically the dam geometry, we can do dam hastening in the order of 1 to 1.5 times the crest width. So we think this is just a rule of thumb. If your existing dam has a crest thickness only of 4 meters, I think it is very problematic if you cannot hasten just by 10 meters. I would say feasible would be about 4 to 6 meters. But our dams in Switzerland, we have a great thickness, as I will show. What are a few further technical aspects is timing of concreting has to be investigated in view of climatic conditions. In our case, in the mountains, and also here in India, in the Himalayas, you may working a period per year, maybe only a few months. Okay. So the next one is the bonding options of new and old concrete. How do you do that? One can do it by anchors. We can do it by dowels of new and old concrete, and we can do it by treatment of the interface by some kind of epoxy mortar or maybe some other techniques. But I would say these are a kind of possible solutions. With higher reservoir level, as I mentioned already, appurtenant structures, spillways may have to be modified as well. And the other point here would be related to differential settlements between new and old parts of a dam, which have to be prevented. Okay, therefore, some consolidation, grouting of a foundation supporting new concrete parts is needed. So these are some of the technical issues which have to be addressed. And as I've said, if you do this modifications of the dam, you must do it according to today's design and safety criteria. Okay, what are some techniques for dam hastening? And I will give a few examples. Number one, rock anchors and post tension anchors. Number two, shear keys at horizontal interfaces. It can be without anchor at interface of old new concrete, or with anchor between old and new concrete. There could be a provision of a slot between old and new concrete, or other techniques that we have a separation of old and new concrete by a membrane. Okay, for example, yes, if you have some special problems. And the number 7 is the connection of different types of materials. It is RCC and structural concrete. This is, let me say, if you have an RCC dam body, the spillway will still be made of structural concrete. That means reinforced concrete. So we have the interface between the spillway structure, which is usually in a RCC gravity dam, is a crest spillway, and the dam body. And we have some connections with inclined dam foundation interfaces. Okay, I will just show a few examples, and then I would say quite useful if somebody is interested is a book, one of the ICOLD congresses, 18th congresses in South Africa, in Durban, it's already 27 years old, was dealing with raising or modification of dams. So if you want to get information on that, on executed problems, I would say I would refer to that very comprehensive volume, which has is maybe 600 or more pages, where you find a number of cases. Okay, so let me just come briefly through with different types of dam hastening techniques. This is now a dam which actually with shape. It has been hastened. Let me say the whole dam body has been hastened, and as you see, it has been hastened from 290 water level 298 to 328. So it is 23 meters, which is quite a bit. This could be a solution here. It is an old dam. It's a masonry dam, which was the height was increased by adding a concrete part at the dam body. The geometry has been expanded more or less linearly, you know, with the hastening. The other one, which I mentioned here, what would be feasible, 1.0 to 1.5 times the crest width. That would be hastening of a dam just here locally without making all these modifications. If you are doing this modification, of course, you can hasten much more. But the problem, as I've indicated there, is basically this interface between old and new concrete. And there is also, as you see in this example, there are different additional works necessary with this upstream facing, also with the grout curtain and with the drainage system. Okay, this is a dam which also has been hastened, I should say. This has been connected, I almost forgot that here, with the rock anchors. So rock anchors have been provided, so by post-tensioning, you can achieve here that you have a compression and you have a good bond here, let me say, at this interface, which we have seen already this morning. The lift joints are usually weak points under dynamic actions. This is another example here with post-tensioning, with heightening, and here only the top portion has been increased, and we see it has been increased about 10 meters water level. Okay, but the dam crest was already quite thin, so it has a modification was done, and I must say the shape now, it doesn't look actually very favorable. It more looks like the Koina arch dam, the Koina gravity dam, where some cracks developed also, where people hastened the dam. It was decided to hasten the dam during construction, therefore it had this shape, which here in this dam in Morocco looks quite similar, which shows here how this hastening is done at the crown cantilever, at the highest cantilever, and here it is closer to the abutment, of course, where the addition of concrete is more prominent than in the center part of the dam. Here it involves modification of the cross section, of course, near the abutments. Okay, some further details here about this post-tensioning of the dam. I just go quickly through that, and I would go to the second one. It would be by shear keys. This is a dam now in Switzerland. It's a Mauvasin arch dam. It had already a width here of about 15 meters, so it is quite high. And with 15 meters, I said we can hasten without problems 1.0 times 1.5 the thickness. So this dam here was hastened by 13.5 meters, which is roughly 1 times the thickness of the dam crest. And this shows how this additional part, this is an arch dam, has been added on top. Well, for hastening, it was now not an arch dam which was added, it was actually gravity blocks were put on the crest of the arch dam. So these gravity blocks do not act basically as will not carry the load as in arch direction, but they will carry the load by the cantilever action. So you can see that, but the detail I wanted to show here is this shear key. Is a kind of a shear key. This is the old crest. Part of the concrete has been removed, so we have some interlocking between the new concrete and the old concrete in terms of sliding, if we look into that aspect. In addition, at the block joints, they have introduced here spherical shear keys. There are about 10, as you can see in this block. Otherwise, you can also use trapezoidal, but I think this at that time people thought this spherical ones are maybe provide less stress concentration. Yes, okay, there are not very strong reasons why we should use that. We have seen now in China, they also used in some dams this spherical shear keys, which some people may think are more advanced than the conventional shear keys, something like that, you know. Instead of round ones, we could have square elements, you know, with like a trapezoidal shape. Okay, now this it just shows the case of interface of modifications of dams. These are just some selected options which are possible. This is an arch gravity dam, so therefore we could add some extra material at the downstream phase, as you can see here in the US, or it is also possible if it is curved to add theoretically a double curvature dam. And if you have a double curvature, of course, you can save a lot of material. These days, with climate change, okay, CO2 footprint and so on, people think concrete should be forbidden. Some people in Western Europe, they think like that. You know, the time of concrete, of cement is over, so one would have to look into alternatives, minimizing CO2 footprint, and to minimize that means to minimize also the materials, not only the type of cement or using fly ash and all this kind of thing. But what I want to say here is, okay, for this arch, 2.93 meters, we would say this is not okay. Okay, it's much too thin. Okay, so people have done some analysis with the showing what is the effect of the heightening of the dam on the stresses in this dam project. Now, one of the biggest project actually which was heightened is the Uri Dam in Venezuela. It is a very big. It is the biggest dam in Venezuela. It was originally built 2 stages. Okay, here you see it was built here, but it was already planned for in the second stage for heightening. So therefore, in the second stage, this part here was added, and it increased the dam height by 52 meters. Is a lot. Okay, so the original dam, it basically almost not quite doubled, but almost doubled the height of a dam. And of course, this is only possible if you have already taken some measures before that you can heighten it. Or it is easiest if you have planned for that already at the time of construction. So you can minimize the effort for this dam heightening. So this is probably the greatest the dam with the greatest capacity which has been heightened. But heightening is quite popular. Let me say, if the construction takes a lot of time and you can already do power production basically during construction of your dam, that you have already some income. Okay, there are some others with heightening a block here, and then there are some anchors or dowels between attaching the old and the new concrete, and in addition to that, here due to some let me say pore pressure buildup, there are some drainages provided here, and in addition we have here these anchor bolts in order to ensure that you have a good connection. The anchor bolts are also a little problematic, let me say. It should be almost of stainless steel, because at the interface, if there is some gap, you may have some signs of corrosion. Okay, these are just a few examples. Also with bolting, this part here has been added. So there are many ways how you can do that, and the connection between old and new has been done by dowels, and they have been grouted here by some epoxy mortar. This is a connection between concrete and masonry dam in France, where also some dowels have been provided to connect that. A case in Japan, the original dam here, some part was added. Of course, if you do this type of heightening, it is almost a new project, and it is basically it is like almost a new dam. We have just done it in Switzerland. We wanted to connect two dams. I will show it also. And rather than connecting a new dam to an old dam, it was decided to build a new dam about 20 meters further downstream. Okay, and just to build a new one, just to eliminate all these problems, because if you do this kind of work, it almost is questionable if it would not just be easier to build a completely new dam if you really have to make that big modifications. Okay, there have been some project. Here is a buttress dam. You see also the buttress. This is the one in Sudan, which I mentioned, which was 18 by 10 meters. It was also planned already at the time of construction in the 1950s to increase the height, because there's a lot of sediment along the Blue Nile. And here you see the web of the buttress also had to be enlarged, and there were some plans with some membranes between the existing concrete and the new concrete. So this dam has actually been completed about 10 years ago, the heightening. So this is a dam in Laos, which we studied. It is now almost finished also. It is just the dam type has been slightly changed from an arch gravity dam to a slightly curved gravity dam, because people have suspected some kind of a clay layer, a thin clay layer somewhere in the foundation. So it moved to a gravity dam rather than having a slope here of 1 to 0.5, which would be the typical slope for an arch gravity dam. It has become 1 to 0.8, which is a typical shape of a gravity dam. But still, the dam is a RCC dam, the green one. And if you have a spillway structure, the spillway is reinforced concrete. It cannot be, because RCC is basically low quality concrete compared with structural concrete. So we have here reinforced concrete, and special attention must be taken how you connect the structural concrete here on top of this RCC dam body. This shows here we have also proposed to have, at that time here, when it was steeper here for the arch gravity dam, we proposed to have here these dowels, these anchor bars, and these anchor bars, these dowels, should be of stainless steel, because as I mentioned already, there could be still this joint between this RCC and structural concrete, and which could be a weak point in terms of corrosion protection. Okay, so let me come to one case. This one is a heightening of this Mauvaisin arch dam, and I just want to say, one of the problems which I've mentioned already is, if you have some dams, you are not really excavating, you just excavate the minimum. So therefore you have also some inclined interfaces, and during construction, if you have some monoliths, there could be some sliding stability issues if you have this inclined interfaces, whereas the stability of a horizontal interface is of course much superior to an inclined one. And the example I would like to explain here briefly is the heightening of the Movassin arch dam by 13.5 meters in Switzerland. It actually, this dam belonged to our company, to our former company, let me say, and we did this heightening project, which was a very economical project, also from the environmental point of view, because you didn't need all these environmental approvals today, you know, in terms of sustainability. Okay, everybody likes to use the term sustainability, but basically it means sustainability is environmental safety. It is related to environmental impact. So with heightening, you can really reduce this kind of sustainability issues today, which accelerates the construction of these projects. I would say today, you know, it will be very difficult to build new dams in Switzerland. There are all kinds of organizations or interest groups which oppose these projects, and through the legal system you can delay projects easily by 10 years. So if you do not have this resistance, like from dam heightnings, it should be lesser, but it is also still a lot of opposition. You can have some benefits. Okay, what has been done there by heightening the dam? I should show that. The idea was just to heighten the dam here, not to make modifications. Okay, just to heighten, because the previous ones I've shown, they changed the geometry. They changed the geometry of the dam, but here, in our case, what we think is the most economical way is that we can keep the dam shape and just add the extra height here on the crest. So that is the concept which we have applied. So what have been the working stages for this heightening? Number one, of course, there was a removal of the crest concrete down to mass concrete of the original structure, because on the crest we have some road. So this part will be removed. Then there will be some proper cleaning of the interface, and there will be moistening of the surface, that we have a good bond between the old and new concrete. Of course, this shall also be done if you do conventional dam construction at the lift joint. You should do the pressure cleaning of the interface and subsequent moistening of the surface to have a good bond at the lift elevation and here at the interface between old and new concrete. And here, as detailed, first they put the 5 centimeter mortar bed, quite high cement content, prior to the concrete placement. Okay, it's some time given that the bond between the old and new concrete and between the mortar is guaranteed. So we have this work had to be done very fast. Okay, this is this dam. This is this Movassin dam, and it is already heightened here. You can see here, this is the heightening of 13.5 meters. It's also in the mountains, could look like in North India. But the dam here now, it is 250 meters high. It is one of the highest dams, arch dams in the world. And when it was built, it was already the highest in the world. But it was built in a very massive way in the 1950s. It's 60 years old. It's over 60 years old already. So it was built very massive, I mentioned already once for those who participated in a previous presentation. I said in Switzerland we also had some design requirements or minimum requirements specified by the military, by the army, and the military requirement for the big Swiss dams is that the thickness of a dam must be about 14 meters, that it is capable of to withstand the largest conventional weapon. Okay, that is, it comes also from the attack of the British to the German dams, but at that time, I think the largest bomb was about 2.5 tons of explosives. Here in Switzerland, we think of 10 tons of explosives. So, based on some studies, it was found out that the concrete thickness of about 13, 14, 15 meters would be required to withstand the blast of a 10-ton bomb. So therefore, for the large dams, where the reservoir cannot be lowered within a reasonable period of time, the thickness of a crest had to be 14, 15 meters. So our dams, large dams, have a very thick crest, and they have extra safety because of this military requirement, which is today basically not required. This was during the Cold War area. So therefore, it is possible to add extra weight to the dam because they have been over-designed because of this military requirement, and we can just put some extra concrete here on top of an existing dam without strengthening the dam body. And as I've said, this is a double curvature arch dam, and also this looks also like an arch. But these blocks which are put on top are gravity blocks. You know, these joints here are not grouted here. So it doesn't act as an arch here. It is just gravity blocks on top of this dam. Here show a few words. Okay, here we see the dam crest. Here you see it is quite thick. Here, that is characteristics of Swiss dams, and you see the reservoir rim is basically almost vertical. Here, these blocks are being built. Here, of course, the blocks, the joints of these gravity blocks are exactly at the same location as the contraction joints or block joints of the arch dam. Okay, so this is here during construction in the early 1990s, 90 or 89, 90, 91 it was completed. Where on this side we also have spillway. There was some modification on this specific type of spillway which was used. The difference between Switzerland and India is, or if I say foothills of the Himalayas, is that our floods are very small compared to your floods. So our spillways are very small compared to the spillways you have in the Himalayas. Okay, here we see, I've shown this photo before, or just a cross section. We see here we have this spherical shear keys. And we have here an opening access road. You can say the top gallery, and it was left open. It was a relatively large opening. Of course, you can save concrete. It's not just on a safe concrete. It is for dissipating basically also the heat of hydration. So with that big opening, you had also better control of the hydration process, heat of hydration of the concrete. Okay, this is it looks the same here. This is the Hayton dam. It's the reservoir empty. This is from a downstream view. This Hayton, it still looks very nice. At least, okay, this is a picture I've taken maybe 20 years ago. But it shows, yeah, or not quite, but it shows here, or what I want to show here is this is at quite high elevation, over 2,000 meters. So the climate is such that the concrete looks quite fresh. Also, it is here already, the old concrete is already at least over 50 years old here. So it looks quite fresh. You know yourself, if you are in the tropical countries, within 2 years, it doesn't look that nice. If you have algae and so on, all kind of things growing on the concrete. Okay, this is once more this cross section. I've shown this access road, which we have built here. This tunnel. So this tunnel is has quite a big cross section. Of course, it is not just for trucks to come through, but it is also, okay, you can minimize some concrete and you can minimize some thermal effects here due to heat of hydration, as I've mentioned already. Okay, because the normal gallery has this kind more or less of an elliptical cross section. This is a gallery used inspection gallery. Okay, this is once more this cross section with these 10 spherical shear keys. So with the shear keys, in the previous example, what I've just shown in the morning was the dam in Turkey, where we have some blocks which may move 1, 2, or even 4 meters. Of course, when you have the shear keys will prevent the relative movements of blocks. These are gravity blocks. It is not an arch action here in this case. Now, of course, people are doing the monitoring, and this here is basically pendulums over several years of the old dam and the new dam, and it shows what has changed basically once you come to the new dam. The red one would be the new one. And somebody asked me once about the deflection of the dam, but here it is very difficult to read that, the maximum. But for this dam, 250 meters high, under full water load, the maximum displacement was, I think, was about 15 or 18 centimeters. So we do not really talk about large, we do not talk about half a meter of a 250 meters high dam. Now this is our dam, which is now being under construction. It had some, let me say, unusual performance. This dam was built in the 1930s, and it was decided, or it was planned, also 20 years ago already, to heighten this dam actually by a lot, 23 meters. And even for heightening the dam by 23 meters, okay, there was a lot of opposition here because it is in a somehow protected. Okay, all these environments are somehow protected, so there has been opposition on this dam for more than 20 years, and it was not possible to heighten it. But I would like to show nevertheless the project we have for heightening the dam. Now, the heightening was not allowed up to now, but the dam had some deficiencies, so either it had to be repaired, and the decision was taken, and the dam is now under construction, build a new dam here. So it's just a few meters, let me say 50 meters or So if you look the distance of the downstream tow with future upstream tow, so it is almost just below this dam. And I would like to show briefly what had been concepts which almost have been accepted. Okay, this is the old dam, and as it was built long time ago, at that time people were not really up to date with controlling shrinkage. So therefore, as you can see, the dam was built here with some individual blocks and some joints left open to allow some shrinkage deformations. And of course, when we have seen this type of construction, if there would be some cracks, seismic cracks development, most likely they will develop along such blocks, such block interfaces. Okay, so this is the dam, how it was built, and there have been shown there were some problems appearing here and some problems appearing here, and therefore, or there were just some displacements increasing as a function of time. So therefore, some remedial measures were required, and at the same time, people come up with a project of heightening of a dam. What do we see here? This is this dam. It looks actually quite, it looks quite interesting. It looks like an RCC dam today, but it is conventional mass concrete, and it is, as you see here, is all this area is famous for this granitic rock. Okay, some picture. It's a breast thickness. Also doesn't meet today's requirement. It's quite thin, but this is just let me say walkway for a trail. Let me say is a trail from here to going to this pass here, which is called Crimson Pass. And you see here there had at the upstream phase, there were done already a number of repair works with some leakage. So therefore, because of these deficiencies, you can also see some aging of this concrete here. Some repair, some upgrading actually was required of this dam. Okay, so what were basically the concepts which were considered? The concept was, that is from 2005, it is 16 years ago, it was decided to heighten the dam here. Okay, this is the heightening, but for the heightening first, they also demolished some part of the old dam here. It was called the red, is a part which was considered to be removed from the existing dam, and on top of that now, the red one being removed, was the blue one, which is now, this here is a arch gravity, we have seen this is an arch gravity dam, but now it was one project was to superimpose more or less on top of this arch gravity dam an arch dam with double curvature. You know, arch gravity dam have only curvature in arch direction, not in cantilever direction. But here now, what is on top is a double curvature, also curvature in the cross section. So that was the idea, to add this dam here and to heighten the dam by this 23 meters. And with that, also the problematic concrete, which I've shown before, could be removed here. So this was a project. The owner was quite confident that this dam could basically be built, but there was opposition because there were also there were about 20 or 25 rare trees which were only growing there because they built this dam already 80 years ago. So because it's at an elevation where otherwise there are no trees. Anyway, some trees were growing, and by hastening of a dam, these trees would have to be cut down, and I must say it's only a small number of trees. Therefore, the project, there are some other reasons, but among one of the most important reasons was because of these 20 trees. Also, as a compensation, the dam owner was ready to plant another 1,000 trees. This was not accepted. Okay, you think in India you have already a lot of opposition for some dam projects, but we think we have even more. Okay, but you do not hear about it. Okay, that's the difference. But here what I show is for hastening, people looked already in some details, concreting, 2 or 3 meters, I think 3 meters probably. These lifts, elevations, and already time schedule was done also for controlling the heat of hydration. And as I'm showing here, a problem, of course, was this interface here between the old and new concrete. And here are just some modifications in the dam geometry, because we thought it is too thin, and it would probably be better also to remove this part here of the dam crest to have a better dam shape. Okay, so we did quite a number of analysis, creep analysis, arch stresses, and you see if you have old concrete, new concrete, taking into account the different actions, heat also, it gives quite some, let me say, unusual pattern of stress distribution. These here are arch stresses in the circumferential direction, and here these are vertical stresses. Okay, so we have done quite a number of these kind of analysis, 3D analysis, and we looked here, for example, we were most interested also in the stresses at the interface between the old and new dam, and this had to be ensured by some rock anchors. Just in here, this is some normal stress. Okay, we can do different types of modifications, but if you do this modification, I would say this case here, what I've shown with superimposing a double curvature arch dam on top of arch gravity dam, of course, is quite unusual. It has been done for one dam, but in this case, this project now, after about 10 years, it was scrapped because it was not allowed to hasten the dam by 23 meters. So the new dam, which is being built now, is having exactly the same height as the existing dam, which had some technical problems. Okay, what are the conclusions? Modification of dams, either to strengthen or to raise them, is done rather frequently. I forgot to say the case of Beauvais Dam, which was 13.5 meters. I think the extra land which was required was only about 10 hectares because the slopes of the reservoir were extremely steep. So it didn't need more extra land. Of course, the dam owner had to buy this extra land. The Greenpeace and so on, World WF, they put the dam owner, we were actually the dam owners, put us under pressure, and they said, okay, anyway, we have to buy this extra land in the reservoir, and they said as a compensation, we have to buy once more the same piece of land downstream of a dam and to convert it in a so-called biotope and to donate this land then to the municipality downstream, and when they would be willing to withdraw the lawsuit. Okay, they will not go on with legal process, which would have delayed the project by 10 years. So we have been basically blackmailed to do something, which we thought, is a kind of a little of borderline. In the meantime, this biotope has been destroyed already by avalanches because these people didn't know where they were. Okay, this is just a side story, but I'm sure in India you know many more stories about people opposing projects and coming up with some strange, let me say, stories and so on. But we also have them in Switzerland, and I would say in Switzerland, I think it is even stricter than what you have in India. Now, number two, raising a dam is often justified when better knowledge of hydrological conditions is available. Okay, if we know if there is more inflow, there are some other projects where people overestimated the inflow and the reservoir is too large. Of course, if the reservoir is already too large, we should not do hastening. Okay, the hydrological situation must be such that this is a feasible project. Number three, most dams built according to well-established design criteria can be hastened. Okay, we feel comfortable. It can be hastened without strengthening actually the dam itself, but the limitations is related, I would say, to, this is just a rule of thumb, related to the thickness of a crest. So I must say, do not plan dams which have a thin crest. It's not a good. Personally, I feel it's not good. Some people in Austria build thin dams, but thin dams have some problems. The most important prerequisite for concrete dams are as follows. Okay, where this is feasible, rock foundations should be of average to good quality, and we should have good quality with proper strength, frost resistance, and no swelling processes in order actually that the old dam still has a long service life. Next one, inspection galleries should be provided at critical locations for concrete dams exceeding a height of about 60 meters. This is a general comment. In addition, additional monitoring equipment should be provided at the interface. Okay, some of these monitoring instruments, they have put some pressure cells, let me say, between old and new concrete at some locations, but I would say pressure cells, the results could not be used. So it is not a good idea to provide pressure cells, but usually people propose all kinds of instruments, and modern methods of construction shall be evaluated, such as pre-stressing anchors, dowels, and so on. So these were a few ideas about the dam hastening, and it is clear if you do the dam hastening, to sum up two important issues. If you do the dam hastening, it has to be done according to the current design specification and not the old one. This is quite important, and some people do not really, I must say, some owners, they prefer to follow the old design guidelines. I've been involved in some nuclear plants. There's already an older one in Switzerland, and they needed a new or a redundant cooling system. And they said, they want to have exactly the same specifications than at the time of the construction 40 years ago. To have the approval of the authorities. So otherwise it would need a new relicensing and so on. If they would follow all the new guidelines, so they rather preferred it to have it upgraded using the concepts which were used at the time of construction. Okay, there are quite a few discussions on this issue, and it is clear between old concrete and new concrete heightening, the corresponding seismic safety analysis will be more demanding than those of a new dam. So let me come, I think we have about 40 minutes more. Let me come to topic number 5 here, which I would like to present. So I would like to say a few words about uncertainties in seismic analysis of concrete and embankment dams, where we have the main uncertainties. I think it is quite important because some people feel we have to do the seismic hazard analysis as accurate as possible. Some other people feel we have to use finite element models to be as accurate as possible, and so on and so on. And of course, if you only improve, let me say, one discipline, it does not improve the, let me say, the accuracy of the results of the analysis, or it does not give a better assessment of the seismic safety of the dam. And I would like to address that. I think it is quite important. If we look into uncertainties in the seismic analysis of dams, we can consider different types of uncertainties. Number one, uncertainties from a seismic hazard and seismic input. And here I talk only, let me say for simplicity, I talk only about ground shaking. Because seismic hazard, what the seismologists basically are focusing is only on ground shaking, and that is also in most cases what the engineers are using. But we do not consider, as I've said, faults, we do not consider rock falls or some other features, which may be even more important. So we have already some uncertainties here, but here, in addition, which I'm not mentioning, but here we talk about ground motion and the uncertainties in the seismic input of the analysis, in the dynamic analysis. Then we have uncertainties in the structural modeling. Okay, finite element models, static models are relatively simple compared to the dynamic models, where we have radiation damping and structural damping, difficult issues which come in addition to the static analysis, which is relatively trivial, let me say, compared to the dynamic one. Number three, we have some uncertainties in the material properties. If you look yourself, for example, in a gravity dam, concrete dam, you have already problems to find information on the modulus of elasticity, which is a very basic property, or the model of mass concrete, or the modulus of elasticity, or deformational modulus, whatever you call it, of the foundational rock. It varies a lot. Okay. Then it is okay, structural modeling. This here is a finite element measure, but then the type of dynamic analysis. The question is, do you account for dynamic interaction effects between reservoir and foundation? Then there is some problems. What do you do with the numerical results? Sometimes at this time we look into the maximum response, maximum stresses and so on, maximum displacements. We only look into the maximum values, but the response is a whole time history. So what are the characteristic parameters you use in a safety evaluation? Is it a peak value, or is it the whole time history? Is it something like low cycle fatigue effects and so on? And then there are some uncertainties into the performance criteria. That is, means what are allowable deformations? I've shown in Turkey, we get deformations of 1-2 meters. Is this too much or not? Okay, who specifies when? So these quantities are also not, are maybe also variable, need some engineering judgment, and different people may come up with different values because these values are not given in corresponding code. So as you can see here, we have quite a number of uncertainties which have to be taken into account in the dynamic analysis and in the seismic safety assessment of dams. And this is only related to ground checking. As I said, other factors even have to be added. Okay, I show it here in some example in Thailand. This shows, for example, sonation. If we do a seismic hazard analysis, we also have a lot of factors which affect the accuracy of the seismic hazard analysis. In addition, what kind of sonation are you using? You would compare historical sonations and with sonations today. You would arrive at different sonations. Today we use different attenuation laws, or we call it ground motion prediction equations. They are being updated periodically when longer observation, more data exists. So these are not accurate, let me say, relations, or these are relations which are being updated periodically. Then there are some questions about return period of the design earthquakes or safety evaluation earthquakes. So there are different people using different concepts here. And in addition, if we look then into the ground motion, it plays a role. What kind of ground motion are you using? Are you considering directivity effect, near field effect? What is the duration of strong ground shaking? What is the effect of aftershocks? And so on. There are a lot of uncertainties already in the seismic hazard itself. You know, I've marked here just in the previous slide, I just marked it by one uncertainty in the seismic hazard, but in the course of the seismic hazard analysis, you come up with a lot of sub-uncertainties, if I may say that. Now, if you look here, this is Mr. I think it's from Abrahamson. He made once a kind of estimation, what kind of ground motion we consider. Do we consider mean value, or do we consider 84 percentile values? That means mean plus 1 standard deviation, or 2 standard deviations, or 3 standard deviations. There are quite some uncertainties, and if you see here the mean value, for example, this is a spectrometric acceleration at the period of 1 second for a magnitude 7 earthquake at a focal depth of 10 kilometers, and we get the ground motion peak value 0.3 G, but the standard deviation is quite large. It gives 0.45 G. If you consider 2 standard deviation, it's 0.94 G. If you take 3 standard deviations, it is 1.63 G. This is a factor of 5 here, as we can see. Okay, so if you define the ground motion is what kind of reliability level of a peak ground acceleration are you actually using. At this time in ICOLD, we say if you use a deterministic analysis, you use median plus 1 standard deviation. You would use these values. But if we use the probabilistic seismic hazard analysis, we say the ground motion parameters are the mean values. And the mean values, well, is slightly higher than the median value, is maybe about 0.4 G. So there are different values being used for different design spectra. And as you can see, the impact of these standard deviations is quite large. And the standard deviation is large. Okay. In addition, as I said, for crustal earthquakes, for example, today people are using this NGA2 West models, if I may call it, in next generation attenuation laws, the latest version from 2014. There are different authors doing different, let me say, statistical analysis and establishing some models, doing calibration with the strongest earthquake. And we see here, this is for earthquake with 10,000 years, using some of the attenuation laws, which are considered very different quite a bit. So therefore, in the practice for the seismic hazard analysis, people are using so-called logic trees that you can give different weight to the attenuation laws by different authors. Okay, usually we do not have this information to give different weights, so we give equal weights to all these different, let me say, ground motion prediction results of different ground motion prediction equations. Okay, so we have already here this uncertainties, and as I've said, the idea is then for the analysis to spectrum matching of the acceleration time histories. And please, okay, if you are not too familiar with the response spectrum, the situation is from the seismic hazard analysis, we will get basically a response spectrum. This ground motion prediction equation allow you to define response spectra for a certain damping ratio and for certain confidence level, mean values, median, mean plus 1 standard, 2 standard deviations, and so on, what I've shown before. So we define these spectra once already, but for the nonlinear dynamic analysis, we need acceleration time histories, but the situation is there is an infinite number of acceleration time histories which can fit this spectrum. Infinite. So it is not so straightforward to select an appropriate acceleration time history. So some people like to use recorded acceleration time histories, which they modify the amplitudes here and some phase shifts in a way that it fits this target spectrum. This can be done, but much depends, of course, what is the recorded accelerogram. I would say for dams where we have some damage mechanisms, like embankment dams, also sliding is a cumulative process. The duration of strong ground shaking place, this is this duration here. There are different definitions, but this duration is the essential parameter. The longer the duration, almost proportionally with time, with the duration, the damage increases almost linearly with the duration. Okay, so therefore, for the engineer, it is very essential to have proper time histories, and the time histories should be on the safe side, if I may call it like that. We could use only this short time history. Probably this short time history, few seconds, we could also match this here, but the damage would be 10 times smaller. And if you would do the analysis with all with the longer duration earthquake. So the duration, I must say, is one of the key issues. So we have a lot of uncertainties in the seismic hazard analysis, as you have seen here. And there are, I would say, battalions. Well, okay, I'm a little skeptical here. There are huge numbers of seismologists working on attenuation laws, working on improvement of seismic hazard analysis. Really a large number. Even more than civil engineering doing dynamic analysis. So, but these people often do not know what the engineers actually need, but they are doing extremely sophisticated models, and I must say, today the models have become so sophisticated, it is even difficult to understand them properly. I have been involved in, I was even at interim for about 1 year, was a project manager of one of these studies, but it is, it was, I would say, it was the world's most detailed study ever carried out. They have spent about 20 million US dollars for a seismic hazard study for 4 sites involving large numbers of seismologists. The result was such that the owners of the nuclear plants were not happy with the result. Okay, even also we have spent 20 million, is a lot. Okay, you can do incredible, a lot of work, and there are a lot of uncertainties and so on. As I said, there are really huge number of scientists working on seismic hazard analysis aspects. So now let's look in the uncertainties in structural modeling. Question, how do you do the modeling of the dam? Do you use how many elements? What the size of the elements? How do you model the foundation, the geological layers, and so on? How do you model the reservoir? Okay, so we have this. Finally, for the analysis, you have to truncate somehow a foundation. There is also boundary element method, but it does not account of basically the local geology in the foundation. It is more for layered half spaces. Okay, so we have this kind of problem with the structural modeling. It's quite a headache. If you do dynamic stability analysis of embankment dams, and if you look into the stability of critical wedges or slopes, there is a question, what is the critical slope which you have to consider? Of course, some people who just look into the results, they will say, you only have to look into the slope which has the lowest safety factor, but for the safety assessment of a dam, this is maybe irrelevant, and often is irrelevant, and people just doing the analysis. Basically, we are interested in slopes like these 4. If this would fail, also the safety factor is here higher than this one here. But if it fails, okay, we will have here water seeping. The water level is higher than the core, so water could seep along this failure surface, and it could create progressive failure, internal erosion of this dam. So for the safety assessment, you would need a slope edge or a wedge, which is critical, which can cause a safety problem of a dam. You do not have to focus on critical slip circles here, which are just in a surface, which have a low safety factor, but it doesn't affect the dam safety. So basically, we have to look into that. So this is also another type of uncertainty. Often I see people just look into the lowest safety factor, that is just a shallow slide here, shallow slide. It is harmless. It's nothing. You know, it doesn't create a safety problem. But if you have a more deeper one crossing the core, where we can have internal erosion problems, it's just much more critical. We have to look in those. Okay, so what are the uncertainties and errors in the deterministic dynamic analysis? Okay, the different types of analysis. We have also discussed it. We have a pseudostatic analysis, does not account for dynamic properties. We have a response spectrum analysis, just combines the peaks of different modes, and it also has some limitations on proportional damping. And we have the mode superposition method. Similarly, we can do a frequency domain analysis, has some advantages for the earthquake input, and I must say the most versatile method which exists is the direct time integration method. So if you have linear, elastic, or non-linear problems, basically it is all direct time integration method. So we have already some uncertainties in the method of analysis. Now this is just a case of, yes, this is the right one, of an example I've shown already a few times. Nonlinear dynamic analysis. We can do also what I discussed already before. In the morning, we can do a dynamic nonlinear dynamic stability analysis, like this arch gravity dam in Switzerland, where people assumed already some of the cracks to have been developed fully. And if you do the dynamic action, it is assumed that before the earthquake, these cracks have already fully developed. And under earthquake, we will have a rocking and sliding motion. And at the end of the earthquake, the upper portion may have moved some distance along this interface. And one would then have to make the assessment if this displacement here into the upstream direction is an acceptable one. Here is just to give you some idea about the sensitivity and the, let me say, the uncertainties in the dynamic response. Okay, this of this problem here. What if you use here different types of earthquakes with the same response spectrum, spectrum matched acceleration here at this location. And if you do that, if you take an earthquake with a duration of 15 seconds, 25 seconds, 32 seconds, and we assume this earthquake acts once from right to left, and once we use the same to act from left to right, simply said, by simply reversing the sign of the acceleration time history, that means reverse. And you can see here 15 seconds if you do the time history, 170 millimeters. If you reverse it, it's even worse, it gives twice the value. 25 seconds, 520, reversed about the same. 32 seconds, 700, 1045. Okay, what can you see here? Basically, that is what I said. If you have damage mechanisms, if your duration is 15 seconds, or if your duration is 32 seconds, the response is basically twice as large. Duration is twice as large, so the inelastic deformations are also twice as large. So therefore, I said in a dynamic analysis, if somebody wants And most people who check it do not know it. If you select just a short duration earthquake, your inelastic deformation can be decreased a lot. If you just take 5 seconds, you may get only 100 millimeters. Whereas if you take longer, you may get 1,000. So it's the duration of strong ground motion in a nonlinear dynamic analysis is a very key factor. Okay, that is with the analysis and the seismic input. Now let me say something about uncertainties in the dynamic material properties. This is just some laboratory tests. You see here, this is for some clay material, and you see we have quite some bandwidth. Please take into account this is a logarithmic scale. So this bandwidth is from about 400 to 2000. It's a factor of 5. It's not small. This is a factor. These are factors. These are not percentage. So in the material models, we have a lot of uncertainties. In the seismic, we do not have variations of factors of 5 in the uncertainties of the seismic input, but in material properties, we can have very substantial differences between upper and lower bound material properties. And similarly, okay, this is what has been used in the analysis for the shear models. Usually we use, of course, lesser variation, but the variation is still relatively large, 0.65 to about 0.45. It's also 40% or so. Similarly, for the damping ratio, which we consider, we also have quite some spreading between the upper bound and lower bound. For a shear strain of 0.1, we get the variation of 20% damping up to about 10% damping. It affects the dynamic response quite substantially. And I've shown that, I think, at the very beginning. I've shown this slide for those doing the dynamic analysis of dams. This is a concrete arch dam in Turkey, also 250 meters. And we have, just for comparison purposes, we have analyzed the stresses in this dam, maximum principal stresses, due to seismic action for empty reservoir. This is the empty reservoir condition, and we have looked into what is the effect of the damping ratio on the maximum stresses, considering a damping ratio of 2%, 5%, and 12%. 5% is typically used in some guidelines, like in Switzerland. 2% are basically the values which you would obtain if you would do ambient vibration tests or forced vibration tests. You would get these low values, and the 12 values you would get if you would follow, for example, US Army Corps of Engineer design guidelines, where people account for, make some estimates on radiation damping into the foundation. Okay, but what is the difference? Just to show you the maximum value, I hope you can read it. For 2% damping, we get 36. This is a linear elastic analysis. So this stress is not a realistic one, but it just shows the sensitivity of the analysis. It gives 36 megapascal. If you have 5% damping, the maximum stress here is 20 megapascal. And if you have 12% damping, here the location is slightly changing. You get 13 megapascal. So if you increase your damping ratio from 2 to 12%, as some people like, you can reduce your maximum dynamic response by a factor of 3. No, it's a lot. This is only damping. This is not the acceleration, time history, and so on. And about damping, quite quite a little. There are not thousands, hundreds of people working on the dam to estimate the damping in arch dams, unlike in the seismic hazard analysis, where many people working on improving the reliability of a ground motion. But there is no need to have a ground motion with an accuracy of 1%. Okay, this will never be the case. And to have a damping ratio, the accuracy is a factor of 3. So if you make an improvement from 10% to 5% in a ground motion, and still material properties have still much greater uncertainties, the accuracy or the reliability of your results will not be improved, will remain basically the same. So you must be careful. Do not think only you shall improve a lot on the finite element model or to improve on the seismic hazard analysis, or also also the material properties. If you do improve only on selected components of the overall safety assessment, it doesn't improve the overall accuracy or reliability of the results of the dynamic analysis. So you have to be careful, but in the analysis, some people believe very much in the analysis, so they have worked a lot on the analysis. In a nuclear plant, for example, people doing the most incredible analysis, and they feel it becomes more accurate, but it is basically not the case. So it must be somehow balanced, that we have some reasonable, to have that the engineer, the dam engineer finally, that he's able to somehow assess these different types of uncertainties. Okay, then there are these uncertainties in the compilation of numerical results. Shall we only look into the peak values, or shall we look in different factors? Because the response is actually a whole time history, and not only one time histories. It is displacement time histories, it is acceleration time histories, okay, and it is stress time histories. So for the whole complex time history, what are the characteristic values you take out of it? Usually people just take the maximum. Okay. And there is a question of a combination of the static stresses with the maximum principal stresses from the dynamic analysis. Why is this a problem? You know, for the static analysis, you use basically, for the static load cases, basically you are using the static stiffness properties, static modulus of elasticity, which for mass concrete may be 20, 30 gigapascal. You will do that for the static load combinations, and then you have to add seismic load combination, but under seismic actions, your E modulus will increase about 25% or so. So therefore, you would have, in your model, you would have to use different stiffness properties, and therefore there is some question also how you superimpose these static stresses with the maximum dynamic stresses. Okay, the direction of the static stresses is clear, but the maximum dynamic stresses, basically, if you have only the dynamic ones, like in a response spectrum analysis, if you have a maximum dynamic, you do not have the maximum principal directions of these stresses. So you cannot just simply the superposition of these static stresses with the maximum dynamic stresses, let me say from a response spectrum analysis, becomes not so straightforward. Okay, it would be straightforward if you do a direct time history analysis with variable E modulus, then for the static and dynamic, it can be done. Okay, that is what I'm what I have written here. So I would say there are some people who are keen in the let me say response spectrum method. I would say today the computational resources are such that you basically it doesn't matter if you do a whole time history analysis or if you do a response spectrum analysis. In a response spectrum analysis, you have a lot of additional problems. If you would do it just in a time history analysis, you do not have these problems, and the computational effort doesn't play a role. So therefore, I would say you better do not do the response spectrum analysis for dam bodies. Okay, this is also has been for already for 20 years, has been a policy in Switzerland. We came to that conclusion. So I think it's also the response spectrum analysis was developed at that time when people had very limited computational resources. So to have a more economic method by using to do the dynamic analysis with just a few modes, but the response spectrum analysis or a so-called pseudodynamic method, we would only apply to all dams. Of course, if you have a dam of 5 meters, you could do this very simple method, but once you have bigger dams, we should do a more detailed analysis. Okay, the last point here is uncertainties in seismic performance criteria. Okay, in the old days, the question was, what are the allowable stresses, edge and compression for different load combinations? It is not so straightforward, you know. If you just have linear elastic behavior and you want to show that you have no damage, therefore you look into some allowable stresses. What are the allowable stresses? Today, I would say if you would do a stress test, for example, we would look into the biaxial strength curve of mass concrete, and we would have to look into basically along the surfaces of the dam where we have a biaxial stress state. We can look if the stresses are within these biaxial strength curves. But the critical zones would be basically tension and combined phases, tension and compression. So there are some problems here, uncertainties with the seismic performance criteria. Also, the question was asked, what are the allowable deformations? Some people have different ideas. Today, we cannot, like in the bridges, where we say, or in buildings, we say span over 500, for example, are the allowable deformations due to live loads. It will be difficult to give such values for, let me say, different types of dams. For embankment dams, we give some values about settlements, but the settlements are basically static settlements. But we know already from static settlements that we have big differences from different dams. Is it 0.1% or is it 1% or even 2%? The dam we have shown Attürk Dam in Turkey, it had about 4%, you know. So damping can be quite variable, but the dam is still okay. Now, okay, what are the allowable sliding deformations of concrete blocks or sliding masses? Also, what are the safety factors? If safety factors are still being used, are we just saying one? But for earthquake case and different load combinations, and if you use safety factors, it is correlated to the strength properties you're using. For example, is it residual strength? peak strength, and so on? Is it with uplift pressures, and so on, and so on, and so on? So there are quite some uncertainties. I call it uncertainties, but these values need basically engineering judgment. It is engineering judgment. Okay, now what we need, because of all of these uncertainties, we need what everybody talks also these days. People talk about resilient dams, because we need dams which can cope with the uncertainties. Because the response can be 4 or it can be 8. So we should not build a structure which will start to fail already with 4, when even 8 is theoretically also possible. Okay, so therefore I would like to show this example. This is basically the Lower Crystal Springs Gravity Dam in the United States. In California, it's not high, 43 meters. It was Hayden then. It was completed, yes, almost 133 years old, and it survived the 1906 San Francisco earthquake, which is a very severe earthquake. It was undamaged, and it was only 250 meters away from the San Fernando Fault. So the peak ground acceleration probably would have been very high, would have been 0.7, 0.8, 0.9 G, I would say, if it is very close to this causative fault of this earthquake. But the dam was built here, as you can see, as I've shown also the dam in Switzerland, with interlocking blocks, because at that time people were not yet able to cope with the shrinkage strain. So therefore you placed concrete in blocks and you have some joints here. Okay. Yeah, construction joints. So basically it is built, it looks like a masonry structure, but it is not masonry, these are concrete blocks. And we can imagine now that this dam, when it was subjected to that strong earthquake, you know, we have a stress concentration here. Maybe we have some higher stresses also here. Maybe due to ground shaking, because this interfaces existed already, it opened slightly, maybe a millimeter, 2 millimeters, and then closed. And if it, under this reverse seismic action, it did not create cracks. Because the cracks are already there. They are these interfaces, as we can see here. So the dam basically was undamaged, because if you have the overstress, the tensile strains will be released here, and they will protect concrete from tensile strains. So if you have this kind of structure, this would be a very resilient structure. Of course, we would also have to check for the sliding stability, but I'm discussing here now just how it would have responded to the high stresses. The high stresses would be released by opening this joint here. If you have high stresses here, you will have some opening of the joint here. And after the earthquake, these, due to the gravity load, these cracks or these joints will close. Okay, I don't have the information, of course, if this repeated opening and closing, if the water seepage when increased or not. But once you have overstresses, large strains, it opens the crack here. It protects also the other ones. It may be not max, I would say only 1 or 2 of these cracks or of these joints here will open. Not everyone here. Only 1 or 2 will be enough to protect the others from developing large strains again. So this, I would say, if we talk about resilient structures, this very old structure, I think when it was built, it was the highest gravity dam or arch gravity dam in a world. Okay, we see here this old photo, Lower Crystal Springs Dam, how it looks like. We see still some blocks here, probably. We see here these joints, how it was built. Okay, now let me come to the conclusions here. Okay, you have a lot of uncertainties in this seismic analysis. So I must say, to cope with uncertainties, I must say the dam engineer must somehow keep in mind that you have a lot of uncertainties. So he should also think what could happen if the seismic action is larger than what has been anticipated, and that means the dam should be able to cope with this larger, let me say, deformations or larger earthquakes than which are assumed in the case of the design or at the time of the safety evaluation of this dam. Okay. Just to go briefly to these conclusions. In dam analysis, models are used that are close to reality. Okay, we would basically like to analyze dams or using methods of analysis which we think are quite realistic. Of course, when you have a lot of uncertainties, you still have some deviation, but it is clear which was one of the questions asked this morning, is if you use a pseudostatic analysis, we predict that basically the dam is allowed, the stresses are within the allowable stresses, so everything is okay, so the dam is absolutely safe and it will be undamaged. But actually, it is correct. So the method of analysis, the pseudostatic method of analysis, does not allow properly determine the dynamic response of the dam. Therefore, it is also outdated. Okay, so please keep in mind. Number two, complex nonlinear analysis and MC ground motions. If we look into that, increase actually the uncertainties in the results. For nonlinear analysis, we have all kinds of, let me say, models. I have not yet discussed the concrete models, but in some of the finite element codes, commercially available codes, you have concrete models. I think some of the models have even up to 30 parameters. You could say these parameters you are never able to obtain. You have already problems in obtaining the damping ratio or even the modulus of elasticity. How you think you can determine the other 31? They are just predefined values. So if you would like to do such analysis, you would have to do, let me say, thousands of sensitivity study and you would never come to an end. Okay, so that is a complex analysis. So I would say I do not really encourage you to use very complicated concrete models. I would say I would say it is a better approach to use simple models, which I have tried to explain here with rigid body models in the case of concrete dams. Number three, a resilient dam design is the most effective means to cope with uncertainties, all kinds of uncertainties. And I've shown the old-fashioned dam there from a Crystal Springs dam is actually would fall under the resilient dams, whereas maybe today's dams may be less resilient than that one, may not perform that well than this old Crystal Springs dams. Okay, selected improvements in some disciplines may not lead to better results. That means sophisticated material models or advanced dynamic dam reservoir foundation analysis may hardly improve the reliability of results. Or not only think of doing improvements on the seismic hazard analysis or method of analysis or whatever it is. If it is just a single improvement and the other uncertainties remain the same, it doesn't improve the accuracy of the results. And I would say, in view of many uncertainties, substantial engineering judgment is needed. And that is a task of a dam engineer, basically, he should have proper experience and he should know basically what are the weaknesses, and he should be aware that he has to cope with large uncertainties if he looks into the seismic safety of dams. So with that, sometimes it doesn't want to move. Okay, with that, I would like to finish, and it is almost, I have to, what shall I say, I have almost to congratulate myself because the time is just over, and there is one presentation which I have not presented, and that is on ground motion model, but you can have a look into the PDF of this presentation. So we have still a few minutes time for some questions. Please ask.
Yes, sir. Thank you for your nice presentation. One question regarding embankment dam foundation. Suppose, sir, if we model a soil foundation under an embankment dam, say 50-meter depth up to the rock, and assign constitutive model Mohr-Coulomb. Then when input motion is assigned at the base of the foundation, then inherent hysteretic damping present in the plastic model works. And we assign only nominal Rayleigh damping 0.2% only to this model. At some predominant, of course, at some predominant frequency. Then in other case, when output at the top of the foundation is taken in this model, then it is not matching with the convoluted motion obtained from the shake software, in which equivalent linear model is used, shear modulus and damping dependent on the shear strain. Then how we can match these two output? What should be the target value?
Yeah, okay. I would say if you have embankment dams on soil foundation, okay, I would say this is a kind of, let me say, unusual case, because if you have an embankment dam on a 50-meter thick soil foundation, you will need a cutoff wall. Okay, you will need a 50, 60 meter steep cutoff wall, which may be already quite expensive to do that. Anyway, but I would say usually your embankment dam would be on a rock foundation. But there are these cases, as you explained in your case, where you have this, let me say, founded on soil. In this case, I would say you do the analysis, you assume that your ground motion is on the rock surface. Your input ground motion is on the rock surface, and you analyze the complete system, the dam body, including the foundation block.
Yeah.
Okay, so you do not have this, you do not have to have this question which you ask. And again, here there are, of course, different methods of dynamic analysis. And I would say the standard method for embankment dams has been a method which has been proposed by Leismer and Sweet. Basically, you use their strain, the shear strain dependent shear moduli and shear strain dependent damping ratios. So this is only one damping ratio, so you would not have to distinguish between Rayleigh damping, small damping, and you have a material damping, which you have. It is there all mixed together. I would say this would be the simplest way. But okay, if you want to do the more, let me say sophisticated, and I must say, if you use that method, which I said from C, strain-dependent material properties, you will find in the literature a lot of data which can be used actually. Now, so therefore, this method is still for consulting companies, I would say, is a good method. We are using that because we have this data. Usually, we do not have the material data. We do some sensitivity studies to account for the uncertainties. But now, in your case, you want to use some more Coulomb model, which has some lesser material properties now for dynamic analysis or CAM-clay method models or whatever it is. And I would say if these models, you basically would then not need to add Rayleigh damping, because the concept you have said is more of a concept people would use for concrete dams. You know, if you do nonlinear dynamic analysis of concrete dams, you would basically assume that your dam has maybe a damping ratio of 1 or 2%, and due to the inelastic deformations, this would be structural damping, 1 or 2%, and you would add the other damping would come from nonlinear mechanisms. So, okay, you can follow your method, but I would then not compare it with another method where you separate with first doing, let me say, deconvolution from the rock surface to the earth surface using the shake models in this case.
So these two output is not matching. Then what should I do? Which one is correct?
Yeah, but correct. Well, I must say, you know, the method which I've said from seed, you have a lot of data. And this method is not so, this is not exact. Okay, therefore, to establish the material models for soils, there are a lot of rheological models which can be used. And I must say, I still propose maybe to use the elastoplastic model. I would say is maybe suitable for the static stresses. Calculate the static stresses, and the static stresses are used then to determine corresponding dynamic shear modulus because it depends on the mean effective stresses. So my proposal would be you use if it is as a consultant, you are from an HPC. So I would say as a consultant, I would recommend you to start with this method by seed. But in some other countries, okay, in the meantime, there are a few computer programs which lack and so on. There are about 3-4 programs which have already some material models, and you would have to make some estimates if you have the information for these material models. But our experience has more been on the Seismic method. It is not that accurate, but we connect this dynamic analysis together then with a Newmark sliding block analysis. It is an approximation. We know that, but the shake analysis, we basically we would do it for microsonation, let me say like that, or if you have smaller structures, because the dam body itself, it's maybe 200, 300, 400 meters thick on a layer of 50 meters. So therefore, I would say the deconvolution, it doesn't really work in this case. The deconvolution would work if you have on a 50 meters foundation, you have a building which has different dimensions than the thickness of the layers, for example. But otherwise, the most, I would say, the most accurate case would be you integrate the dam body and the foundation into the same finite element model. But the discrepancy, okay, I don't know your results. I cannot really tell. I'm also not let me say foundation expert, but I can say our committee, there is now a bulletin or a draft is already in the review on the dynamic analysis of embankment dams, which has been prepared by USSD, US Committee on Dams, and my committee will take it over and develop it further into a guideline for ICOL. So there would be somehow the state of the art, because the method by Steve Leisner, it is already 50 years old. And there is a need, I understand also from you, that there is a need for higher accuracy or better reliability of the results of earth structures. And I hope with this guideline we are working on, I hope we can come up a step further.
Okay, sir.
But it doesn't exist yet, you know.
Thank you.
I don't have it here at hand to give it.
Thank you, sir.
People are working on that. They have been working for a long time on this problem. Oh.
Okay, thank you.
Any further question? If the participants still have any more questions, they may write to us. We will arrange and get back to you individually over the email after getting the respective answers from the speaker. Mr. Vivek Tripathi, your hand are still raised. Do you want to ask any more question?
Well, I just have to say, okay, after these 5 workshops, I hope still some people were ready to listen to all my lengthy presentations. It was, I would say, it was a good opportunity for me also somehow to explain what I would call the state of knowledge from the viewpoint of ICOLD. I must say this is not really the state of the art in research, but how we can deal with this, let me say, quite complicated problems in a practical way and in a comprehensive way. It is very important because if we omit something, I would say it is the consequences have been very substantial, and I hope I have been able to bring that over. I also hope that you have kept in mind, I must say, there were a few key statements which I have made and which I have repeated a couple of times, and which I would, as a final comment, I would mention once more. Number one, which is very essential for dams, is that the seismic hazard is a multi-hazard. it is not just ground shaking. So those who are doing structural design, they would have to learn something more. It is not just ground shaking. Secondly, we have to keep in mind that for large dam projects, we have a safety philosophy which is just much more sophisticated and what is being used in normal building structures or other infrastructure projects where we consider structural safety, dam safety monitoring, operational safety maintenance, and emergency planning. We have to look into all aspects also from a seismic point of view. So I would say these are the key elements you should not forget. And otherwise, I must say the details I've given to explain the different issues. And maybe the last point I would also like to emphasize, or last 2 points, is that the time of a pseudostatic method is over. It has been over for a long period, and I hope you have realized this fact. And the second other point here I would like to address is that the service lifespan of dams can be very long. It can be easily be well-built dams, 100, 200 years in my opinion. And during this long lifespan, there will be several seismic safety evaluations which have to be carried out at this time. A dam which has been built during the time of a British 100 years ago, let me say, it doesn't mean it is safe today. Okay, it has to be checked. For example, if it satisfies safe criteria. So please keep that in mind. So thank you very much.
Yeah. Yes, Dr. Martin Wall. Yes, Dr. Martin. Yeah, it was a wonderful experience to have learned from your experience of 4 decades and plus in the comforts of our office. And we are really, learned quite a few things, because I understand from your pictures and project descriptions, you have a hands-on experience on large number of dams across the world. Maybe the person of your stature are not many across the world, and it was really good. So we are grateful to you that you have agreed to give such an online lectures, so that we didn't have to travel, or you didn't have to travel. But I am pretty sure that the pleasure of learning was as good as if we are listening to you in person. So I'm very thankful to you. We hope to meet you sometime.
Yes. Okay. Thank you.
On behalf of INCOL and on my personal behalf, I would like to convey my special thanks to Dr. Martin Wieland for sparing his valuable time and agreeing to our request for conducting the series of 5 virtual workshops for 2 days duration. He's always very kind and helpful to INCOL for organizing such activities in the past. I'm sure all the participants have benefited from his vast knowledge shared during the virtual program. I'm also convey my sincere thanks to ICOL Vice President and President INCOL, Mr. Devendra Kumar Sharma, Vice President INCOL and Member DNR, Central Water Commission, Government of India, Dr. R.K. Gupta, Secretary General Mr. Aditya Kumar Dinkar, for the guidance and support to organize such activities for the benefit of Indian dam professionals. Thanks are due to all dam professionals for their time and participation. Thank you all. Stay safe, stay healthy. Goodbye.
Okay.
Thank you, sir.
Okay. Okay. Thank you very much. Yes.